I'm Chia-Che, and in this part of the tutorial, I will cover the architecture overview of the Graphene Library OS. The Graphene Library OS architecture is built on top of an untrusted host to run an unmodified Linux applications inside a trusted environment. This means we can support native executable and library without any code modifications or recompilations. The whole application will be protected inside one or multiple enclaves. And inside the enclave, there will be several other layers, including the Graphene Library OS itself. This is the separate layers, and the platform adaptation layers designed specifically for this host. So why do we focus on supporting a modified Linux application, and how do we do that? Well, think about Apache Web Server. This is a classic example of a modified Linux application because in this application you can find all kinds of different binaries, including the modules and libraries such as crypto library and traditional systemc library like libc and pthread. So to support all these binaries, like you actually need full support for dynamic libraries. You need to have a dynamic loader to load these binary into the trusted execution environment. And from the user perspective, they don't necessarily want to recompile all these modules and libraries into one single binary. One reason, of course, is because they want to be able to load these binaries as needed. But also, they don't necessarily they don't necessarily have the source code needed for the whole recompilation. So supporting unmodified Linux applications become the core concepts of Graphene Library OS. Of these Graphene Library OS is to implement these Linux system calls inside the user lands. We all know these Linux system calls are usually implemented into the kernel space. However, from the perspective of these enclaves, they don't necessarily trust the kernel to provide the right Linux system call results. Therefore, we do need these library OS layers inside enclave to support these Linux system call features. So the way we do it is we introduce a modified C library. In other words, the libc. The libc will have change all the places they make system call and forwards all the system call into the Graphene Library OS layer. The requirement of this technique is to have all the system calls made through libc. If the system call is actually made by the application binary itself, for example, through inline assembly code, then in that cases we do need other ways of capturing all these system calls. But anyway, if these system calls are forwarded into the Graphene Library OS, then they can be served by the Graphene Library OS system call component. And these system components will either implement these Linux system call internally inside the library OS, or they will use this platform adaptation layer to translate it into the host API. In this case, it will be Linux system call, and to go to the untrusted host operating system and use to actually access these OS features. So as you can see, these platform adaptation layers with PAL actually has a very important role in terms of a layer for translating a narrow API needed by the Graphene Library OS to implement these OS features into any host interfaces possible. So in these cases, you can consider for the Graphene Library OS, they will try to handle most of the system call functionality internally. But if there's something they cannot handle, they do have to interact with the host operating system. They'll use this so-called PAL calls, which is the narrow API defined by the platform adaptation layers, and they will translate it into the host environment's host API, their system API. The requirement here is for each host environment, such as SGXs or Linux, they will need one unique PAL designed specifically for this host environment. The most simple example of PAL is the PAL we built for the Linux host. This PAL is very simple. It simply translates the PAL calls into the Linux system call necessary. So you can use this PAL to debug the library OS itself, because at this point you probably don't want to involve SGXs. You simply want to see if there's any issue with the library OSs, then you can run with this Linux PAL. You can think of, for example, if the Graphene library OSs want to, let's say, read the file, they can issue PAL calls to this Linux PAL layer. At this point, there is no unclip protection whatsoever in this mode, because this simply is designed for running the whole application with Graphene library OSs inside a Linux process. So this Linux PALs will translate the PAL calls into the Linux system call, such as the read system call, and they will return the file content back to the library OSs, and then eventually return back to the application itself. However, the PAL you really want to use for confidential computing is this SGX PAL. This SGX PAL not only translates the Linux system call, but also it can shield your Linux application inside the enclave from any malicious Linux system call results. So think about the same scenario when Graphene library OSs want to read the file, they issue PAL calls to this SGX PAL layers. Because the whole Graphene library OSs and SGX PAL will run inside enclave, they will be protected from the untrusted host. And then the SGX PAL will have to do a number of things, including it would jump out of the enclave, and then it will actually make system calls with untrusted host operating system. And then once they receive the system call result, they will forward it back to Graphene library OSs. And before returning the system call result, they will have to sanitize any result that are potentially malicious. This will ensures that even if the untrusted operating system is acting maliciously, it returns malicious system call results. It will not affect or corrupt the behavior of the Graphene library OSs and the applications. And here's a quick overview of the Graphene library OSs itself. As you can see, it has pretty much all the components needed for operating the system, including multiprocessor or multi-threading features like fork and threading, file systems, sockets, pipes, and as well as inter-process coordinations such as namespaces and signals. So far, we have pretty much implemented a majority part of the core features for to support Linux applications, including supporting 145 system calls. These are the core features of a Linux operating system. The total size of the source code of the Graphene library OSs is around 246,000 lines of code, and if you compile this source code, the binary size will be around 1.2 megabytes. And so that will conclude this part of the tutorial. Thank you.